Okay, so we have discussed about histogram manipulation and spatial enhancement of images. Okay, uh, for improving the visual quality of image, for extracting the various features like edges. Okay, and to eliminate the noise component. Okay, now we have another component to be discussed, that is image classification. So in image classification, we automatically categorize all the pixels which are there in the image into land feature classes like vegetation, water, sand, soil, road network, etc. Okay. So in image classification, it is processed, that is we use to produce thematic maps of imagery. Like in this photograph, you can see that we have a water channel, there are the road network, building, grass field, etc. Okay. So while image classification, we categorize them into the major classes. Okay. So once we generate the major classes, a unique color is given to those class. Like if we talk about water bodies, so one unique color is given to the water body. Similarly, when we talk about road network, a unique color is given to the road network. So while image classification, in the input image, the representation is in 8-bit, but once you generate a classified image, so that is represented in terms of thematic maps. So one feature is represented by one color. This is the workflow that we adopt for image classification. As you see that from a particular scene, by using sensors, the images are collected in multiple bands. Okay. Now using those bands, let's say we have a k band, total number of bands are k in number. So out of k, a subset is selected first. Okay. When we select a subset of bands, they are used for labeling. They are used for generation of thematic maps. Okay. So we perform a training. In training, what we do, the subset of image, okay, that is selected, in those spectral band, we collect the response of various objects. Like let's say out of 12 band, we select uh, green, red, and NIR band for the classification. Okay. So out of 12 multispectral images, 12 band multispectral images, the subset that is comprised of 3 bands in green, red, and NIR, they are selected for the classification, keeping in mind these 3 bands are having highest information from that scene. What we do further, like there are various objects in the image, we want to generate a thematic map for them. We perform a training. In training, what we do, we know that a particular, by visualization, we know that, okay, if there is a red pixel, this red pixel belong to which object. Okay. Like in our earlier discussion, we talk about vegetation has highest reflectance in NIR band. And let's say the red color is given to the NIR band. It means if you see the color image, red pixels are representing vegetation. Okay. So based on the background knowledge, we know that wherever red pixels are there in the image, they are representing vegetation. So what we do, we select a training samples. Okay. While training sample selection, we just pick the red colored pixels. Okay. And we see that what is the digital number for those pixels in red, green, red, and NIR band. Okay. Similarly, from overall image, we select the vegetation training samples. Similarly, for the water, for uh, soil, for the bitumen that is used for the road construction, for the grass field, okay, they are selected. Once we have a training samples corresponding to these objects, those training samples are plotted in the k-dimensional Euclidean space. KD, and then further we form a decision boundaries. We'll see it later on. Okay, and after that, uh, after this training, what we do, from the input image, one by one pixels are selected and they are compared with the training samples. Okay, and finally, on the basis of comparison, we see the closeness of those pixels to the training pixels, and we assign them the class that we call the labeling. And finally, thematic map is generated. So overall, how it is done? By the user experience, by the field visit, what we do, first we select a training samples. Like when we have image in 3 band, red, green, and NIR, in those 3 spectral band, we first select a training samples corresponding to vegetation. Let's say if our intended class which we want to generate are vegetation, water, and soil, 3 class. Okay, so what we do, through the training, we select a digital number in red, blue, and NIR band from vegetation, from soil, and from water, either from the image itself or visiting to the field. So the training samples, we know, after collecting the training samples, we know that these set of digital numbers are representing vegetation, and another set of digital numbers are representing soil, and while the third set of digital numbers are representing water. They are plotted in uh, 3-dimensional Euclidean space. In this case, we have a 3 band. Then decision boundaries are formed. There are different ways to form the decision boundaries, or there are different ways to utilize the training samples to match them with the input selected pixel. So once training is done, what we do, from the image, one by one, a pixel is selected. If I talk about over here, the pixel, the pixel is, if we have selected 3 spectral band, so a pixel is represented by a column vector. Okay, that is 1 cross 3. So each row is representing digital number corresponding to respective spectral band. So the first row, it's a digital number in green band, second row digital number in red band, while third row digital number in NIR band. Okay, so one by one, each pixel is given as input to the training model, trained model, and output is generated in terms of just labeling from to which class that pixel belong to. And it is done on the basis of analyzing the closeness of that input pixel with the given information in the training sample. As you see in the image, it's not a 3-dimensional Euclidean space. For better explanation, only 2 bands are taken over here, band B1 and B2. And 2-dimensional Euclidean space, training samples which are collected. Okay, collection of training samples means we collect a digital number in respective bands. Here we have 2 band B1 and B2. So in this 2 band, training samples are collected. So it can be done by the field experiment, Okay, you need to go in the field by using a handheld uh, sensing equipment. You need to just collect it. How much a digital number, how much energy is there, and what is the digital number that is generated. So band B1, what is the digital number? Band B2, what is the digital number? Okay. So for three class C1, C2, and C3, the pixels are collected in terms of digital numbers in band B1 and B2, and they are plotted over here. Now we need to draw a decision boundary. Like when you select an unknown pixel, let's say an unknown pixel is selected over here and it is marked red in color. Okay. If the red marked unknown pixel, and from the given information, you need to assign it to the class C1, C2, and C3, how it is done. So when we are going to respond how it is done, okay, at this place, we have categorized the different approaches to do it. We'll see it. Again, I will take this into the consideration in the next slide. I hope it is clear to you. Right now, I'm talking about training-based classification. Like you need to collect the training samples from the actual class, either from the images or from the field. And after collection of training samples, they are plotted in a k-dimensional Euclidean space on the basis of digital numbers corresponding to their spectral band. There are two major classification approaches. The first one is spectral pattern recognition. In case of spectral classifier, what we do, we use a set of radiance measurement in various wavebands for each pixel. Like when we select a vegetation, okay? So we analyze the radiance from vegetation. Let's say we are having three bands. So what is the radiance from vegetation in red? What is radiance from vegetation in green? And NIR band, as I discussed before. So on the basis of actual digital number, that is representation of radiance we are getting from those GRCs. Okay. This spectral classifier work. Second category we have, that is spatial pattern recognition. So it works by using the geometric relationship of a pixel with its neighborhood. So in spatial classifiers, they consider many aspects like image texture, pixel proximity, feature size, shape, directionality, repetition, and context. In our discussion, we mainly concentrate on spectral classifiers. So there are two categories, supervised as well as unsupervised classifier. In supervised classifier, what we do, using some training samples and their ground correspondence, we define a decision rules. Okay, as I said before, in this case, this is an example of supervised classification. Okay, where from the field or from the image, the ground truth is collected. Like when we talk about vegetation, then we need to calculate in three spectral band, red, green, and NIR, what are the digital numbers which we get from the vegetation. Similarly, so those digital numbers which are well distributed in the image, they are selected manually. So the digital numbers, they are the number only, but we know that from which object they belong to. While the training, we collect a digital number, we know that they belong to vegetation. Another set of digital numbers, they are a pixel, they are collected, we know that they belong to a soil. And third set we collect, we know that they belong to the water. Okay, and they are plotted over here in two-dimensional Euclidean space. It is given. It is depicted over here for the simplicity. Okay, not only two, we can go with a K spectral band. So once we plot, once we have generated the training samples on the basis of digital numbers in the training samples, decision rules are defined. And on the basis of decision rules, we categorize supervise classifiers into various classes, various categories. This is the basic step that is illustrated over here through the workflow. In the first case, multi-channel data, multispectral images, 5 bands are given. Okay, and through the training, for the 6 classes, we have generated a training samples. Fine. Now, a known pixel is selected. Okay, and that is compared with the training data, and on the basis of closeness. Now I will define what do we mean by closeness. Closeness is estimated by which parameter? If I talk about closeness to this particular class, so statistically, if we consider the statistical parameters, which parameter we are considering over here to define the closeness? But okay, we'll see it. On the basis of closeness of a chosen pixel to the training sample of these 6 classes, they are labeled to a particular class. Now, the second type of classifier we have unsupervised. In unsupervised classifier, we do not perform the training first. What we do, a clustering is performed by natural grouping of pixels. Like we know that in one of the case, the problem that is given in the quiz, the bimodal distribution of histogram is given. Okay, so if I ask you, what is a natural grouping? So if distribution is bimodal, it means there are two separate group of clusters, two group of pixels cluster. So one group of pixel cluster is representing the low distal number, while another group of pixels cluster are representing the high DN number. So it is called as natural grouping on the basis of magnitude of distal number, okay, which are centered, different distal numbers which are centered over at one particular point. Okay, so in this way we know that if let's say there are vegetation, so vegetation pixels are close to each other. Vegetation pixels, they are respond in red, green and NIR band similar. It means they are clustered at one location in 3-dimensional Euclidean space if you plot them. Okay, so in supervised classification, what we do on the basis of similarity in the distal number and through the natural grouping, the clusters are formed first, and after the cluster formation, the class is assigned to those clusters. So it is a reverse way. In unsupervised classification, we don't know, we don't have a training samples. Okay, by statistical analysis, statistically natural grouping is performed on the basis of similarity in distal numbers, okay, for various objects. The clusters are generated, and finally those clusters are assigned to a class. Okay, so in supervised classification, the first stage is training stage. So what we do, we collect a ground truth. It means if I say vegetation, we select distal numbers for vegetation in our various spectral bands which are used for the classification. To assemble a set of statistics, we collect a training sample to determine a set of statistics that describe the spectral response pattern for each land class type. It can be like once you plot the training samples, just you need to close them. Like in this case over here, let's say if we consider class C2. So minimum bounding rectangle can be plotted over here. Minimum bounding rectangle means in class C2, what is the minimum distal number for band B1 and what is the maximum DN number for band B2? Sorry, band B1. Similarly, what is the minimum for in band B2 and what is maximum in band B2? Using these four vertices, coordinates are calculated and minimum bounding rectangle is plotted. So minimum bounding rectangle means within that rectangle, all the distal numbers are confined for class C2. Similarly, MBR is plotted for C1 and for C2 both. So what we have done, we have enclosed the training samples for class C1, C2 and C3 by a rectangle. So that is called as decision boundary over here. There is other way. There are various ways to form the decision boundary. This is one way I told you. Now, while the training stage, it has to be carried out for all the classes that we want to classify. Okay, and the training statistics should be representative of class concern. Fine. So once we have a distal numbers for various classes, using those distal numbers, we can calculate the statistical parameters. We have already seen that statistics of images. So there are various parameters like mean, variance, standard deviation, mode, median, variance, covariance, matrix, correlation, coefficients. So all these are the statistical representation of training samples of various classes. Theoretically, n plus 1 pixels in a training samples for n band. Okay, let's say if we have a 3 band. Okay, so if we have a 3 band, it means 4 training samples each class. But practically, we'll go with the 10n to 100n pixels for a better representation, for a better statistical representation of a class using training samples. And while collection of training samples, as you see in the image, the training sites from where we collect the training samples, they should be well distributed in the image. Okay, it is not like at one location you have collected all the samples. It's if there are vegetation, so vegetation are distributed in the site, in the test site. From each location, which are well distributed in the test site or in the image, the training samples corresponding to vegetation have to be collected. Similarly, for water and soil. For example, I have considered these 3 classes, these 3 objects which need to be classified in the image. It is for the simplicity only. Okay, now while this training, you need to be very careful that spectral classes should be pure. Like if you are collecting vegetation, so pure vegetation training, pure vegetation pixels need to be selected. Like when you are considering a GRC for vegetation representation, so that GRC should has only the vegetation. It should not be a kind of mix of soil and vegetation. Similarly, when we are considering water, so it should be water only. When we are considering soil, it should not be mixed with other objects like grass, etc. It should be pure soil. Okay. Finally, the class statistics as required is ready at this stage. So once you have collected the training samples, the statistical parameters are calculated like mean, variance, covariance matrix. On the basis of decision boundary that we determine, the first classifier, supervised classifier, is minimum distance to mean classifier. As you see in the image, in a scatter plot in band B1 and B2, training samples of three classes are represented, C1, C2, and C3. What we do, for each C1, C2, and C3 class, their mean values are calculated. For a given training samples of class C1, what is the mean value? For C2, what is the mean value? For C3, what is the mean value? Now, in minimum distance to mean classifier, our input pixel is selected that has to be classified. For that selected input pixel, it is compared with the mean value of class C1, C2, and C3. Okay, in terms of distance. Like let's say for C1, if the mean in band B1 and B2, if it is coming out to be, let's say a DN C1 B1 and DN C1 B2, and the input is selected DN1 and DN2. A pixel is selected, okay, and that pixel is having DN1 and DN2. So how distance is calculated? It is a square root of difference of DN C1 B1 minus DN1. You need to take square plus again this DN B1 minus DN2 square. So the distance is calculated. Two-dimensional Euclidean distance we call. So 2D Euclidean distance is calculated, and the least distance that we get. Okay. So the input pixel is assigned to that class. As you see in the image, it is a small red dot. There are 2 points are represented over here in the image. One is represented by small circle, while another is represented by large circle. Okay, and they are painted by red in color. So they are a known seed pixel which are selected from the image, and they are to be classified to this minimum distance to mean classifier. Red dotted small circle is close to C2, while you can see that the red dotted big circle is close to C1. Okay, so on the basis of closeness in terms of distance from mean, the unknown pixel is labeled to a class. Okay, so a small dotted red circle is close to C2, so it is labeled class C2, while the red dotted big circle unknown pixel is close to C1, so it is assigned to class C1. So closeness we see over here only considering the mean value of training samples. We are not considering the standard deviation. We are not considering the variability. Because see, if you look at the image, if you see the boundary of C3, so is red dotted small circle is close to boundary of C3 compared to boundary of C2. If we consider the standard deviation of pixels in C3, so in class C3, variability is more, variance is more, while in class C2, we have a least variance. It means nearly all the pixels are concentrated to the mean value in class C2. While the highest variance we get in C3, it means the pixels are scattered from the mean value. Okay. So variance is highest in class C3. Least variance we have in class C2, while the variance of class C1 is in between C2 and C3. It is evident from the graph. Okay, so from minimum distance to mean classifier, as you see in this case, two-dimensional Euclidean distance is measured. We can also consider the variance into the consideration, and the plane Euclidean distance that we used to assign a known pixel to a class, we can also consider a variance into the account, and we calculate a modified distance, and that modified distance is Mahalanobis distance over here. Okay, and in this Mahalanobis distance you can see that mean is considered. So a known pixel x minus class K mean multiplied by variance covariance matrix inverse, and further multiplied by the unknown pixel subtracted by mean transpose. Okay. So in a general case, we consider a pure two-dimensional Euclidean space, considering only the mean value of the training classes. While in Mahalanobis distance, along with the mean, we also consider the variance. Okay. Now, when we use different decision rules on the basis of defining different way of estimating the closeness, we have another type of classifier, that is parallelopiped classifier. Okay, like in two-dimensional Euclidean space, I told you, like generate a minimum bounding rectangle. But minimum bounding rectangle, same logic we apply. And if we consider the 3D, like if we are having three spectral classes for the classification. So in three spectral classes, one pixel is having three digital number, each from a class. Okay. So the minimum bounding rectangle is now converted into a parallelopiped, as you see in the figure. So within the parallelopiped, that is exterior boundary, within which all the training samples are located. Like urban area, if you see, so from the urban area, the training samples which are collected, they are lying within a parallelopiped corresponding to urban area. Parallelopiped corresponding to training samples of urban area. It means within that parallelopiped, all the training samples collected from urban area are concentrated, are confined. And the parallelopiped is measured on the basis of what is a mean DN and max DN in all three spectral bands. Okay. Now a known pixel is selected from an image, and it has to be classified to the parallelopiped classifier. How it is done? So decision boundary is formed. So here decision boundary is in terms of exterior boundary of a training samples that is represented by the parallelopiped. So what we do, we select unknown training samples, and now we see that in which parallelopiped it is located. So let's say if it is located in urban area parallelopiped, so that known pixel is given, is labeled as urban pixels. If they are located within the forest parallelopiped, they are labeled as forest. And let's say if we select a pixel that comes outside of the all the given parallelopiped, so that particular pixel is unclassified. But let's say if there are variance within a training sample, so there is a possibility of overlap, like two parallelopipes are overlapping with each other. As you see in this case, in 2D space, uh, the training samples are plotted for class A, B, and C. Like a spread of class A, by using a spread of class A parallelopipe is over here. The minimum bounding rectangle is formed. Corresponding to class B, a MBR is formed. Similarly for class C. And you can also notice the overlap region. Let's say if a pixel is falling within that overlap region, then which class you need to assign that pixel. So this problem occurs in case of spectral, in case of objects for which in the training samples there are high variances, or even if we are having high covariance between the class. High covariance between the class means those classes are correlated with each other. It means when you select a training sample and you plot them in a Euclidean space, so they will overlap. So what we'll do, we perform a bespoking. As you see in the bespoking means we step the boundary regions. To the bespoking, now it is not a kind of minimum bounding rectangle. The overlap region is step down. So to the bespoking, what we do, the area that is overlap, okay, so that overlap region is further divided into the separate class, okay, to the bespoking. So step boundary rather than a regular boundary, now the boundary is stepped out. So creating a step boundary regions, however, becomes impossible or difficult. The bespoking process through which we convert a regular boundary to step boundary region, it becomes difficult if the covariance between the object classes are very high. Okay, and many classes are overlapping. Okay, this is very difficult to execute. Now, in such cases, we have a maximum likelihood classifier. Okay, so maximum likelihood classifier uses both variance as well as mean value to assign a known pixel to a particular class. But what we assume over here, once we collect a training sample, we consider those training samples are normally distributed. Okay, and after the training sample collection, we calculate statistical parameters like mean, variance, and covariance matrix of all the classes. Okay. In this case, probability density function, like let's say if I consider the vegetation. Okay, so distal numbers which are collected from the vegetation, in this case they are plotted for band 3 and band 4. So we have calculated the mean value for that and variance. So using mean value and variance, you can generate a probability density function. So PDF talks about what is the frequency distribution of, in this case, the z-axis represent a frequency distribution. B3, B4 represent from where that pixel is. If I consider only vegetation, and let's say 50 pixels are collected from vegetation. Okay, so we'll see in band B3 and B4. Okay, if let's say I consider 1 pixel, so if out of 50, 4 pixels are same and they are represented by one set of DN number. There are 10 pixels which are represented by another set of DN numbers. Okay, so 4, 10, this is a frequency distribution. Fine. And in this way, they are plotted over here. This is called as probability density function. Now the maximum likelihood classifier, how it works, when we select an unknown pixel, okay, we calculate a likelihood of belonging to a particular spectral class. Okay, and it is computed using the probability density function of the normal curve, which is parameterized using computed mean and covariance matrix. In all the previous cases, like in minimum distance to mean classifier for computing the distance, Mahalanobis distance I considered, where we have taken into the account the variance covariance matrix. But when we consider a normal two-dimensional Euclidean distance or Euclidean distance in KD space, only mean is considered. While in the parallelopiped classifier, we consider only the maximum and minimum value of distal number in that particular training samples. Okay. Further, we do the bespoking to generate a step boundaries to avoid the overlap cases. Now over here in maximum likelihood classifier, what we do, we consider all the statistical parameters. They are mean, variance, and variance covariance matrix. So mean, variance, and covariances, all these parameters are taken into the account to assign, to label an unknown pixel to a class. And the likelihood function is calculated, like in this case, for k band, k number of band. So we have been considering k over here, the 2 and 3 in our discussion for the pictorial representation. Likelihood function using k band information for a known pixel x is calculated as 1 divided by 2 pi n by 2. Okay. So I would like to correct one thing. K is representing a class. Okay. So KD space. So K is representation of which class we are talking about, and N is representation of number of bands we are considering for the classification. Okay. So the likelihood of belonging a pixel, known pixel X to a class K is calculated as LKX. It is equal to 1 divided by 2 pi over number of band n divided by 2, then modulus of variance covariance matrix and power 1 by 2. So the variance covariance matrix into exponential minus 1 by 2. And now just see over here, x minus mu k into variance covariance matrix inverse x minus mu k. Now this is the Mahalanobis distance we are considering over here. Okay. So this likelihood function is calculated. So this likelihood function, you will get a magnitude that tells us, okay, what is the likelihood of class X belonging to, what is likelihood of unknown pixel X belonging to class K. So this likelihood function is calculated for all the classes which are there, for which the training samples are collected. So belongingness of unknown pixel X to a spectral class K, K values of likelihood functions are calculated. Okay. And the unknown pixel X assigned to a particular class for which this likelihood function magnitude is highest. Okay. Uh, Fine. I have a query. Let's say we have a five classes in the image. So how many different variance covariance matrix we have? We want to classify an image into 5 classes. Okay. For each classes, we have collected a training samples. While calculating the statistical parameter, for 5 classes, how many different variance covariance matrix we have? Who will tell me? Arun, could you please unmute?
Yes, sir.
In this query, we want to classify an image into 5 classes. Okay.
Yes, sir.
ठीक है?
Yes, sir.
So when we want to classify into 5 classes, so obviously we need to select training samples for those 5 classes.
Yes, sir.
Okay. So 5 different set of training samples we have, each representing a class.
Yes, sir.
Then after that, what we do, we calculate a statistical parameters for all those 5 set of training samples. So how many different mean value we'll get?
Sir, 5.
Correct. For each class, for each set of training samples, we get one mean value. And that mean value is representation of that class. So we'll get 5 different set of mean values. Similarly, how many different variance covariance matrix we have?
Sir, 5.
5. So taking into the consideration training samples for one particular class, we calculate variance, we calculate mean. Now after that, in each band, okay, like we are considering kth band. So in each band, by taking decimal number in 2 bands, what we calculate? We calculate variances. Then after calculating the variances, we calculate variance covariance matrix. So mean, variance, variance covariance matrix are the statistical representation of a particular class. And these parameters are calculated using the training samples which are collected for that class. So in this query, the K is the representation of class LKX. So to calculate this parameter L over here, we consider the mean value variance covariance matrix from the kth class. So this likelihood function is calculated for each class, considering a known pixel into the picture. So if you see the right hand side, in the right hand side, a known pixel is the variable, while the mu k, that is mean, variance covariance matrix, number of band L, all these are the known parameters, and they are calculated from the training samples. Okay, so the likelihood function is calculated, and to classify an unknown pixel into a class, it is assigned to a class for which the likelihood function is having magnitude highest. Okay,